This is the topic of fields and forces. First, we are going to look at gravitational fields. It takes 2 hours and it will take around 10 minutes to cover the main points. So, gravitational fields. We have to state Newton's universal law of gravitation. Now, everybody knows how the story goes. Newton is sitting under a tree and an apple falls on his head. This is the way the story goes. Then he discovers gravity. But what he realized was that this force of gravity, which is the thing that causes things to fall downwards, was also the same force that keeps the moon in orbit. It was also the same thing that keeps the Earth in orbit around the sun. This was the connection that he made. He saw that the force that was happening on the Earth was the same as the force that was happening in the heavens. Heaven and Earth were ruled by the same laws. And this is a big step forward, especially considering the religious situation at the time. So Newton is famous for this discovery of gravity, rather linking the effect of gravity that we notice on the Earth to what was happening in the heavens. So we know that gravity causes a force on an object that, when it's an unbalanced force, will make things accelerate towards the Earth. If it's not supported, a thing will accelerate towards the Earth. It's the same force, this gravitational force, that provides the centripetal force that keeps the moon in orbit around the Earth. The moon is travelling at a tangent to its orbit, but there's always a force roughly at right angles to its path which makes it keep into a circle. However, Newton knew how big the force was, but the moon was going much slower than it should have done, which means the force was much less than he expected. So he realized that the force of gravity changes with distance away from the object that is pulling it. So in other words, the further away from the Earth you go, the less you're going to feel the force of gravity. And he was the first one to come up with this. And this is basically, the force must drop off very rapidly with distance. This mass is pulling this mass must be pulling this mass with the same force. M1 pulls M2, M2 pulls M1. And this force will be equal to a gravitational constant G times by the product of the masses, and is inversely proportional to the square of the distance between the masses, or between their centers of mass. And this is how we usually write it. F is equal to gmm over r squared. Now normally we have m, the first capital M has been the larger mass, and small m has been the smaller mass, but it makes no difference. The masses could be the same. The force will always be gmm over r squared. So there we have it. It's proportional to the product of the masses and inversely proportional to the square of the distances between them. The universal gravitational constant, G, is 6.67 times 10 to the minus 11. See if you can work out which units they are. Isolate G and then plug in the units to all the other variables, and you will get the value for capital G. Define the gravitational field strength. Now we know that different objects feel the force of gravity to different extents. An apple feels a much smaller force than a person. If you weigh an apple, it weighs 3 newtons. If you weigh a person, it weighs 800 newtons. How can we standardize the force? So we basically have to say, what is the force for every unit of mass, for every kilogram? And this is what the gravitational field strength is. What is the force per unit mass? What is the force per kilogram? Each object has a different weight. Gravitational field strength is independent of the mass of the object. So we define this term, gravitational field strength. This is a force per unit mass that is exerted on an object. So here we have, this is a force per unit mass. This is a force, which is gmm over r squared, divided by mass. Now this can be simplified. We can divide by m and they cancel out. So we end up with F over m is equal to gm over r squared. So G, which is the gravitational field strength, is gm over r squared. This is the gravitational field strength. Small g is equal to gm over r squared. Now, another exercise is that you might determine the gravitational field due to one or more point masses. Okay, so we have to assume that the mass is a point mass, because it makes the calculations much easier. There are two forces acting on this small mass. There's a force due to this one, and there's a gravitational field strength due to this one. We know the gravitational field strength generally is gm over r squared. So what is it going to be, the gravitational field strength due to mass 1? It's going to be gm1 over r1 squared. So this is going to be the gravitational field strength due to mass 1. And on the right, we're going to have the gravitational field strength due to mass 2. So what will the small mass feel? Well, it will feel a force which is force per unit mass, which is the difference between these two, because they're in opposite directions. You have to subtract one from the other. If they were in the same direction, then you would add them, but they're vectors. Gravitational field strength has direction. It is a vector. It's a vector field, so we have to subtract them. So we end up, the total is g1 minus g2, since the direction of the gravitational fields are in opposite directions. Another problem you might get would be to find the ratio of g1 to g2, in which case you do gm1 over r1 squared divided by gm2 over r2 squared. You'll find that the capital G's cancel out, and it ends up being something fairly straightforward. Derive an expression for gravitational field strength at the surface of a planet, assuming that all its mass is concentrated at its center. So we make this approximation that the mass is concentrated at the center. The gravitational field strength is gm over r squared. G is the universal gravitational constant, m is the mass of the planet, r squared is the distance from the center of the planet, but r in this case is the radius of the planet. So we can substitute the r, capital R, which is the radius. So the gravitational field strength at the surface of a planet, gm over capital R squared, is equal to g. And on the Earth, the value for g, or rather the value for gm over r squared, is roughly 9.81 newtons per kilogram, or meters per second squared. Now, the thing about having a point mass is that all points in the Earth contribute in a small amount to the gravitational field strength. So this object here, pulled by this part of the mass here, and here, and here, and here, and here. But when they add them all up, treat it as if the mass is concentrated at the center. Now, this is what the gravitational field would look like on the Earth's surface. Now, these lines are the field lines. Notice that they go downwards, because any force, any object, any mass will feel a force which is downwards. That is a force felt by mass. Notice that the lines are equally spaced, which means it's a constant gravitational field in this area. The field strength is constant. If you go far from the Earth, you notice that the lines are not parallel. You notice that they're quite bunched together close to the Earth. That means the field strength is quite high compared to a magnet. Remember, when you have the magnetic field lines by the poles, they're very much bunched together. This means that the field strength is high. When the field lines spread out, that means that the field strength is low. Fairly close to the Earth, they're almost parallel, but not quite. You can see that they do start to diverge.